What we've covered so far in this class is a very simplistic and very partial coverage of linear regression with gradient descent. If you were ever to try and use linear regression to solve a real-world problem, there are a lot of additional considerations that you would want to think about in order to seriously implement linear regression with or without gradient descent. First of all, gradient descent is only one implementation of linear regression. There are a bunch of other ones, and in some sense they may be better. Ordinary least squares, for example, is always guaranteed to find the optimal solution when performing linear regression, whereas gradient descent is not. Additionally, we haven't really talked about parameter estimation and putting confidence intervals on those parameters. In the models that we've built, we've given exact values for all of our thetas, but as you can imagine, there's some confidence that we have in those values. You can imagine doing more thorough statistical analysis and saying, what are the confidence intervals on these parameters? And we could answer questions like, what is the likelihood that I would get this value for this parameter if this parameter actually had no effect on our output variable? We also might worry about issues like over or underfitting. This isn't so much a problem with linear regression, but with more complicated models, you might expect our model to overfit. Say we had some data like these red points that was approximately linear. If we had a model with many different parameters, we might be able to fit the data points exactly, whereas the actual underlying model is this black line. One way to deal with this is usually to split our data into a training set and a test set. Then we can train a model on the training data and then test it on the test data, just as the name would imply. This is called cross-validation. We might also see underfitting, where we have data that's clearly nonlinear, but we only try and fit a linear model to it. This is also a problem that you might encounter. Another issue worth mentioning again is that our cost function may have numerous local minima. That means that when using gradient descent, our algorithm can become trapped in a local minimum that isn't actually the global minimum of the cost function. This isn't a problem with other implementations of linear regression, but when using gradient descent, this means that maybe we perform gradient descent numerous times, randomizing our initial values of theta with different random values every time. You may also already know this, but when using a random number generator to generate random values, it's important to seed your random values and to store that seed. That way you have a result that's replicable, and other researchers can look at your findings and also produce them on their own machines when they run the same script. This has been a whirlwind tour of a bunch of additional considerations that we didn't really touch in this lesson. These are all really important in machine learning, statistics, using linear regression in the real world. I really wanted to focus here on just implementing gradient descent and the basics of how it works. But if you really wanted to use any of these things to solve a real-life problem, you'd want to think about local minima, other implementations of linear regression, the confidence intervals on your parameters, and if you're using a statistical modeling package in R or Python or Stata, they'll usually give you these confidence intervals and use a reliable implementation of linear regression.